Hello, boys and girls. So there's various ways in which I could pitch to this topic. I will go into a demo in a minute. I just want to say my motivation of this is really, on the one hand, writing another search tool for my personal wiki, but also the fact that recently there were a lot of AI-supported mathematical proofs where a main part of it is really getting references and finding stuff in the literature. And I was thinking, how easy is it actually to have a tool which goes directly to the references and not have the chatbot internally, associate and find this stuff. And it turns out it's extremely easy, basically vibe coded things together. I spent a lot of time on the data, of which we will also talk a lot in this video. But basically I will tell you all the libraries and the specs to do this yourself, and basically you can build this on your own. It works extremely well. It basically worked out of the box. It's super fast. So we will 100% see more of this just because how easy it is. Certainly certain tools in this direction are out there by someone, I'm sure. But if you look, for example, at the Stack Exchange bot that I find very annoying, or other search functions which are I think less impressive what I put together here over Christmas. I think there's a lot to do, and this is also not the end of it for me. I will improve further on this. So just want to say that the second part of this video is Wikipedia as such, but also the math part as training data. What I can say, how the distribution of topics is on Wikipedia. We will see tables like this. Here, fun fact: what is the most viewed statistics articles in statistics in the custom statistics category that I created. We will see a bunch of these plots by which you understand the history and some of the inner workings of Wikipedia as data set, and how to get this and how put all the components together. But okay, let's jump into this demo that I talked about that is pitched in the video title. I start up the Python script. It loads vector comparison. It loads transformer model, and then I'm in this chat environment. I can type any sentence that I want, dump any text that I want. I like transforms of 3D space, and instantly it gives me the Wikipedia pages here that are in content closest to this short sentence that I wrote. It works better if I have more text entered. In this case, at the moment, how I put things together, it's limited to 300 words roughly. But this just depends on the model. I didn't want to go over half a gigabyte model with this case, but I will extend this. So this short text is matched to transformation matrix Wikipedia page, the Wikipedia page called transformation matrix. Then there's also list of coordinate transforms. These are all Wikipedia pages that are associated with this, and it makes sense. I talk about the output in a second. I just give you some other example. I can do 6 is not a prime number, and then it will give me a bunch of Wikipedia articles on that have to do with primes. Okay, this is super boring. I'm interested in time series filters for text calculations, and as you would expect, it gives some autoregressive time series stuff and filters and all this stuff that is associated with this. I have one example prepared where previously I just searched for Fermat's theorem block and picked the first thing that showed up on Wikipedia there. If I take this text that is there, I can of course also dump it in here, and then as you would expect, I get to Fermat's stuff. The Wikipedia, as we will discuss in some length in this video, has its own very fine-grained categories. They are, for classification's sake, not so useful because they are so close to the articles. But every page here is associated with a category. And what I also do here is I count how many times the main category, main Wikipedia category as I defined it, shows up in the top 30 in this case. But what's more towards a proper classification, I have also defined my own custom categories. I'll talk about this a little bit later. I've basically classified all of math Wikipedia in about 20 categories. Here you see computer science, algos, analysis, abstract algebra, these kind of things. And it tells me this text is, very fairly confident here. This is number theory stuff. So implicitly, you can view it as a search function, a reference function, but it's also a classifier of any text, really. It tries to match which category is this closest to when it uses the Wikipedia dataset. Okay, so before we go on, I forgot to mention, I will also contribute this whole video to the Core 1 Kurcha Mungail video series, which is on Python, physics, AI, philosophy, and so on. Okay, so in this video I will talk about sentence transformers. This is the main tool that is, hip and fashionful, and I will explain on a level, it's not very laden with formulas here. I tell you what you need to know to understand how to actually, copy whatever I did and understand why it works. And then there's a bigger part about Wikipedia and where you find some fun results as well. Okay, so what are the components? The transformer that I use is the S-Bird, derived from Bird. It's like a Google product, Google idea from the last 10 years. I have here, then, you can just go there, but you can also, you can ask the chatbot to get all of these things together and combine them, and it will do it for you as it did for me. I use the similarity search, why you will see in a second, but this is also like a Facebook product, and this is also on GitHub, if I recall correctly. Yes, I think so. Also, the nice thing about Wikipedia is that I'm not at all the first person to look at some Wikipedia statistics. I suppose they were not really previously concerned with just looking at certain super subcategories, in this case math. But there are like projects which already package the metadata. For example, I downloaded 30 gigabytes of these categories and how the whole graph looks. All of this has been packaged, and you can also just pull it. And Wikipedia has an open API where you can say, hit this article, what are the categories, what are the neighboring categories, and I jumped around a little bit to get information about the Wikipedia data set graph. So first I discuss the technology of the transformer. Here, audience question, what does ChatGPT stand for? Okay, here in this video, we need the pre-trained transformer part. As you saw, it's not generative. It's not like producing data. It doesn't produce text. I'm not using a transformer that tries to predict the next word. I'm just basically using the embedding part. And now comes a few slides of motivation why this works a lot better than just matching words. And this is not like high level. Don't come at me. I will skip the whole transformer architecture part. This will just be a one write error. In this case, in this way, you can read it by analogy, right? So, for example, I talk about English word, but it's, of course, it's really token, which are more like syllables. But I try to make this more user friendly for the guy who just wants to pull everything and vibe code things together. You start out with your words or syllables, your token, that have a certain embedding at the start. One for each word. All of this is determined, even the initial embedding before you even pipe the data through the transformer with all the mechanisms, attention mechanisms, and so on. This is some vector in a high dimensional space. I will say R to the 800 in my case. I just picked a model which I knew would run fast. I could go higher on this machine even, but this is sort of the ballpark of the dimensions. I will keep on saying word, right? So again, don't come at me for simplifications. The words are mapped to some point in the R to the 800. This is a start point. The embedding is determined in the training. I will not talk about the training as ChatGPT suggests. This is pre-trained. I didn't have to do any training. I can just download the model and run it. But this initial embedding obviously is not all we want. But we have a bunch of words, for example, the word cat, which is embedded at the start as this 800 dimensional vector, 800 floats. And then the transformer action maps it to another vector in the same dimension, as per my explanation here. This notation is basically statistics notation. I thought I will, because I used a bunch of R for the project, and I talked with a bunch of statisticians to who know R better than me. I was like, I will cast the notation in standard R or statistics lingua, so that these people have the easiest access to this video. So that's why I write it down here. Like the word I write down as the first column here. My sentence is the cat chases hungry the mouse. Some random sentence. So this will be a 6 times 800 matrix of floats. These floats are all in the interval -1 to 1. And then what the core part, this transformer does, it maps it to another such sized data set. And then very roughly speaking, to embed the whole sentence, we basically here in the end will average over the columns, and then we get another single 800 dimensional object that represents the whole sentence. Again, this is like a little bit of a simplification there. There's like masking even in this final process and so on. And there's a lot of things you can do, but I will not go into this part in this video. Okay, what does this mapping do from the left-hand side to the right-hand side? So roughly speaking, it takes semantic understanding that is baked into the weights of the transformer and attaches it to the output vector. So I say the cat chases hungry the mouse, and we know that chasing has to do with running, and the mouse is the person who is fleeing here. So there are direction in the vector space, like the being frightened, like associations like this, which are also baked into the output vector. Again, this is a little bit of a simplification, but you must think of it in a way that out of the context of the input sentence, you get more information from the pre-training into the output vector. So if I write I like transforms in 3D space, right, then this internally, because of the SBIRD transformer model having been trained with all the internet available data and maybe more, there are already associations with linear algebra, with matrices, with rotation, like things that you would also associate with it, are being appended to the output, even if these 6 words do not contain the word frightened, because semantically this is like the understanding of this sentence. This notion of frightenedness, so to speak, is attached to the output as well. And so this is also why this search works better. I say transform in 3D space, and then there are, rotations are associated with this sort of sentence, and therefore the search works better with finding Wikipedia articles that actually, for example, talk about quaternions or rotations or whatever we saw in this example. Okay, and so one word about how these words like frightened are represented. I have here this screenshot from a video from a YouTuber called 3Blue1Brown. Has like a big math channel, makes animations. And this is also like a standard example where you have the final embedding of queen and of king, and there are some points in this high-dimensional vector space. I represent it here with 3 dimensions, or rather 3Blue does. And the thing to take away here is that the relation between the king and the queen in the space, they are close, similar. This yellow vector is similar to the relation between man and woman, or uncle and aunt, or like this sort of gender swapping of words. Like there is like you can think of it as there being like a sensible direction that represents this component, this female or feminization, you can think of it. And even if we have a vocabulary of only like 200,000 words, this latent vector space, this abstract vector space, has more points that are relevant information, or more directions with which encode things like the mouse being frightened. Since it's taking being frightened from the context of the mouse being chased by the cat. If I just exchange one word, right, hungry, for Jerry, then because the training data knows of Tom and Jerry, the cartoon series, you get different associations, right? So you, for example, the output vector, and I split this up here in this 6 components. It is maybe better to think of it as a sort of average in the end, because what we get out is really just one vector. So you should not overinterpret my quotes unquote association between different words. But the important point is that by this 2017 attention mechanisms, the context plays a role to give you these new directions and give you like a strengthened coding of your sentence that depends on context and associations in the real world found training data than just matching words, right? Like the naive Wikipedia search algorithm that would just take transforms in 3D space and searches, hey, in which Wikipedia article does the word transforms and 3D space pop up the most, would be like a weaker search tool, and probably also even slower. Okay, and here are some more examples, right? If I say apple is red, I will think of like an apple to eat. If I say apple USB cable, then I think of maybe my own laptop. And while the starting embedding, what I started with, these dots in 800 dimensional space, the token start at the same place. After the transformer call, after I hit enter and all the things run through in my script, the context associates completely different directions here, right? So if I talk Apple USB cable, then we talked about apples, but in the end, this will be associated with charging and electric power, whereas here this will be associated with fruits. I think fruit was one of the examples of the words on the initial slide as well. So this is just to show that the same word can play a different role, and the system is set up for it to be much smarter about this. Okay, and this was like my transformer sketch. I will tell you. I already told you which tools exactly I used. The vocabulary size really is not 200K, but it's more like in several K quantities. I told you the dimension that the tool that I used. In this case, I didn't bother to average like do any chunking and add things together just because it worked so perfectly already out of the box. But I will do this at a later point. The tool that I used over Christmas just has half a gigabyte, but I think it's reasonable that you can, if you want to have so much of your computer dedicated to this sort of tool, you can ramp up to this sort of numbers. Here is like very roughly how much like some of the largest Llama 3 models use. This is like roughly this sort of size, ballparking. Okay, and at the data set that I used, what did I do? For this search, I selected a bunch of Wikipedia pages and embedded them all. And the hard part really was getting, not getting all of the Wikipedia data. Getting all of the Wikipedia data is actually easy, but finding out what is really math was more of there was more work there, and classifying it, and for my further goals. I ended up with this 40K or so Wikipedia pages. So this is under a gigabyte, which is funny because the link data that I downloaded from this EU project already has like 10 gigabytes, which I haven't used so far. And this pulling of data, both of the packaged metadata as well as the pages, and then embedding, all of these steps, they roughly take like 2 hours. Just so you have an idea, you can do this also in a weekend. Okay, so I will start talking about the shape of the Wikipedia data. Here you see like one example of some LLM training data. So there's like smaller LLM training data, for example, even on GitHub, that you can download. And I had a look at, if you want to use this to make anything maybe science and math related, how much of this is actually science and mathy? I wanted to know. So here you see on the slide, oh no, I'm running out of battery. Here you see on the slide rough distribution of this particular data set that I looked at. I looked at a few and did some averaging, but so you have an idea. Roughly 4% of that might be, for example, Wikipedia if you use these data sets. And of Wikipedia, only about 15% or so will be actually STEM relevant stuff. There's a lot about, this is like very rough categories, but you get an impression. Oh, and of course, on this point, I also want to thank all the contributors to Wikipedia, which of course somebody had to write the text that we were making use of here, right? And then of this STEM part, we are going down to about 15% mathematics, right? So it's 4% times 15% and 15%. So we're narrowing down of the typical data set that the data set that I used here represents of training data for some experiments. And still, this is 7 million pages total, Wikipedia. Like, by the way, the EU project metadata snapshot is from 2021. It was during COVID. For some metadata stuff that I used, so for example, all my plots that show views or creation date, they ended 2021. The data that I actually pulled and looking at the categories was live as it is now. I ran, however, into this problem of, what is actually a math category? So what is it, like an article in a math category? Wikipedia has its own sort of somewhat historically grown categorizations. And it's not like there's like a Boolean that says, oh, this is a math article, this is a physics article, because it is also not so that this is like a clear distinction, right? So, for example, if I look like at Euler-Lagrange equations, clearly it's math, but clearly it's also physics. So that clearly this is not as sharp. And so what they have on Wikipedia is a bunch of categories, and I will show you in an example in a second. So as a matter of fact, there are like 2 million categories last I checked, something in this range, right? So, which is actually crazy because it means like there's like a single digit number of pages per category. You will see some examples how fine-grained it is. The example that I will use here is the article on Benford's law. This is again some stats factoid. Everybody has already been on Wikipedia a million times. You know, there's links. These pages are linked together. What you might not know if you're not a Wikipedia contributor or HADA user is that if you scroll down to the bottom of a Wikipedia page, then you come to a categories section where you have all the Wikipedia categories to which this article belongs, right? So, for example, we see that Frank Benford, the creator, inventor of Benford's law, is in the category optical engineers, and a category for people who died in 1948 and so on. If we go back to Benford's law and scroll down, then we will see Benford's law is in the statistical laws category, probability distribution category. If I click statistical laws, then we come to another page. So a category is also just a page with the particular type, if you will, of being a category, and you always have this. I don't know if this is now cut off or not in the recording, but basically all these categories, the names of the categories start with category and then colon, and you see here that the inside of this category statistical laws, there are pages, but this page, which is of type category, also belongs to another category, which is another page called statistics theory. And the statistical theory category page hosts links to a bunch of other categories. So for example, there is like a category called statistical randomness. If I click it, then the statistical randomness category has a category called random matrices, which does not have subcategories but has about 20 other pages. So this is how it's structured, right? Everything is a page. There's like 8 million pages. A lot of them are actually just these category pages, which collect a bunch of other pages at the sites, which are elements of the category. Categories can also hold other categories, right? So this is how the categorization works. There's one category which is called mathematics. But it just has a handful of subcategories, and as you've seen, the categories are really refined. So there are actually 2,000, 3,000 math categories, and part of the job is to sort of find them. Just a statistical fun fact here. So math categories have roughly like around 15, 16 articles, as opposed to a generic Wikipedia category, which has less. Okay. Yes. So how did I go about getting the data? Well, I went to the math category that I just showed you, and then I used the API in an internet-friendly way to like run it overnight, and then just look at which categories is related to this, and do a BFS walk roughly to depth 4, 5, 6, and see which categories are categories of this, and I just walk the category graph, right? I go to all the Wikipedia pages and see which categories do they belong to, and how quickly it takes me to actually jump out of what I would consider mathematics, right? If there's like an economics page which has no formulas at all, it might be, it may be relevant, but it may also be like out of the scope of what I'm interested here. So I pulled all this data, I made some tables, I inspected it manually, said, this is something I want, or clearly I want information theory, I want computer science. I also, in this case, ended up taking programming language stuff, but it gets a little bit fuzzy if to what extent I want actually have this data set, at least for this presentation. Similar with physics, with chemistry, you drift off fairly quickly if you walk the category ways. And then further, I define keywords by which I pull like by which I say a category. So almost everything that has geometry in it or algebra, I will want like a category that has algebra in it. And thankfully, some of these categories are named in a way that if it's algebra, it has like also algebraic or something in the title. And I have like basically 1,000 keywords that enable me to hold on to categories, and I have these custom categories where, for example, I say, convex hull algorithms. This is like far too fine as a category as to be useful for my categorization of texts. And so I package this into this algos numeric geometry category, of which I have like 20. Right? I have mathematician, algos, and analysis, and I take the math categories and package them in there. And I iterated on this and saw, what do I want, what do I not want. In the end, I will expand this. I will also take physics and these kind of things into account. After all, I'm a physicist. But I thought as the first project for my, low power model, I just use pure math plus a little bit computer science. Okay, and I will now show you a little bit about the Wikipedia data content, viewed as a data kind of thing for my custom category, which is probability and statistics. The subcategories on Wikipedia that are biggest are the stochastics processes category, for example, right? So this is like a Wikipedia category that has like over 100 pages associated with it. And then you have, there's oceanographic time series is like a category, but it's like a category with like 2 pages. That's how Wikipedia is. I guess a little bit homegrown and historically grown. Here you see also like a problem I have with sort of overlap, for example, right? So there's categories like algebra, abstract algebra. I think this, it was like 20 years people created this. I mean, you can make a case that these are different things. You could make a case that abstract algebra is a subcategory of algebra, but maybe by algebra people maybe think of or include more like school or lower degree algebra. So it makes sense that there are so many categories because things are also blurry. And of course, there's geometric algebra, algebraic geometry. They have clearly overlap. Like, if you take polynomials, where do this belong? Where does it not belong? Here you see that, for example, algebra has 135 pages in it. And you see then, but for example, that algebraic geometry has over 400 pages in it, and it has like an overlap. So there are like 5 pages which both belong to algebraic geometry and also algebra. And so you see there's like an overlap and a little bit of you could phrase it as like a fight for pages. And it makes it a little bit difficult then to also like take a page and say, what is the main Wikipedia category for this, which was also one of the motivations to create my own category. So this is just an idea what you will struggle with and what you have to think about if you take these data structures and do something with it. The fact that this is like a somewhat complicated graph. Yeah, here this is like from my API calls where I look at the literally thousands of categories. So there's norm spaces, function spaces, overlap spaces. This seems to be like I was in a spot in this graph where it's about function spaces and associate things. So here you see the granularity basically. Okay, here some more fun graphs. So Wikipedia, of course, was started here around 2000. This is just the 40K math pages, but it's very representative, I would say. You see that it had its heyday around 2005. This is where most of the articles were written. And it flattened off. But thankfully, we have to say, it's not like Stack Exchange that it completely died down. People are still writing Wikipedia articles. Here you see the log of the total views versus creation year. Of course, it makes sense that, for example, if an article is older, then it had more chance to be viewed more often. And you see this trend also here in this graph. I have pointed out the points where our example, Benford's Law and Frank Benford pages are. You see, for example, that Benford's Law was like created very early on, and then it took like 5 years or so till its creator got also the biography page. I will also mention that there are so many biography pages, like basically 20% of the math articles are biographies of mathematicians and associated fields. Here in the bottom you see the length of articles, in this case in bytes, and how many times they were viewed. You see the trend is that longer pages are also more often viewed. Which direction this correlation goes, who knows. Yeah, I showed you this before. I did this basically for all my 20 categories. I will not show you all of them, but here I just went for statistics and AI because this is relevant maybe for the viewership of this video. You have normal distribution, Monty Hall, all the favorites, right, are also most viewed. Here in the custom category that I called AI, the Wikipedia page to machine learning, deepfake, uncanny valley. Roughly what you think would be viewed most often. The cutoff here is again 2021. Here computability, it's difficult to, there's like information theory, computer science, CS, programming languages. Computability is something I care for. Foundations. That's why it made it into its own category, and then I had to choose what Wikipedia categories to bunch into this. So there's like a selection aspect to it, but you can see here the computability points. Mathematicians. This was a little bit funny. The most viewed mathematicians under my metrics. Here we have actually Uncle Ted over Da Vinci or Newton and so on. In case you don't know, this is the Unabomber. Okay. Here you see the year of linked citation of the article. So we see here that more recent articles, so scientific articles that are used in Wikipedia pages, are linked or referenced a lot more often, like used as citation. Which makes sense, I guess, just due to the production of articles. There might be this bias here. Okay. Yes, and then there's some fun facts here, for example. Again, all these numbers depend a little bit on what you consider a math page, and so I go by my categorization. But here in my categorization, the longest true math page is here Magic Square, which is, this thing where the columns and the rows are always the same. And you can see this is like a ridiculously long article, which happens to belong to the categories, the Magic Square category. Okay, you see, the thing has its own category. Okay, and the smallest one you see here. So I have excluded from the smallest one disambiguation pages and these kind of things. Here, I'm pretty sure in no time, if some Wikipedian sees this video, that might be a little bit improved from not being the shortest page. So maybe there's a Streisand effect. Okay, and here I have not updated my presentation, but I also looked at basically views per age. Right, because if the pages are older, then they have more time to get views, so it's a little bit of cheating. So views per age per length. So this is basically a characterization of, despite the article being long, it's not really viewed. And here the winners are these sort of articles, of which there are so many, where people categorize like certain more esoteric, let's say, or more like specific structures. And there's like these categories, and there are so many of those, right? You can click around here and you get to the next one, and it never ends. There are a bunch of these. This is like a bug. I didn't update this, but I can tell you the math page which has basically the best view to age to length ratio is the article on the unequal sign. Yeah, I guess it makes sense. It's a very like universal kind of thing. There's also disambiguation pages, which are a little bit of a cheat, right? Some pages are like this, the word has a little bit overlap with concepts. One which also fared very well is semi-definite. The disambiguation page for semi-definite matrices. So the more you know. I want to point out that there is also Wikipedia records, like stats Wikipedia page in itself. You can visit this and you see longest articles and so on and so forth. It's not like STEM or math specific. And there's also a cool page where you can actually see the views, I think even, per week or per day, where you can go there and say, in this case, search for differential equations on axiom of choice, and then you see how often are this viewed. And I know that I think people use this maybe even for trading or whatever. So I think this page views site is also not particular to Wikipedia. You can just get information about how things are viewed, which is interesting. Okay, and with that I come to the end. So I will keep on working on this project because this tool is just so nice. I want to develop it further into math prompt generation tool. If you do anything this direction, let me know. If you want to talk about these kind of things, I'm going to do more like podcasty content. Or if you want to work together, I'm super interested in this, even like freelance in this direction. In particular with scientific research, AI supported tools, writing them and or doing the research itself, contact me. I will expand this to a larger model, so it's easy to load and use models which can read a lot more than 300 words, and you can also do a bunch of tricks where you chunk and do things together. I will integrate this in my own wiki notebook, which already has like search functionality. I used these transformers for some time now, although not with Wikipedia. I use them for my own stuff. And also prompt generation. I already do automatic prompt generation, but now I will aim at supersizing this a bit. And yeah, I think with that, I hope this was informative. I will very likely do another video where I break down the distribution of math for mathematicians, for people who are into STEM, for physicists, because I didn't say half of it. Here, there's like a lot to be learned. At least it's going in my interest. How what are stronger fields on Wikipedia, which are weaker fields, and I have all this data, a bunch of information. I have like a miles long R script which looks at all of this, but I will keep it in under 45 minutes, which is nice for my standards, and will quit the video here. So thanks again, and see you at a later point.